Fine. So, its proof is easy, it is not difficult. So, let us consider the case 1 first. Assume that f prime changes sign from minus to plus. Intuitively we have seen how does it happen. We want to show that f x has a local minimum at x equal to c. So, suppose it changes sign from minus to plus, then that means there exists a delta, a neighborhood, where in c minus delta to c f prime is 0, less than 0, and in c to c plus delta on the right side neighborhood f prime is bigger than 0. That is the meaning of changes sign from minus to plus. On the left it is minus, on the right it is plus. Okay. So, this would say f prime x less than 0 means f x is decreasing on c minus delta to c, and this greater than 0 will say it is increasing on c to c plus delta, and that shows that f x is greater than or equal to f of c for every x in c minus delta to c, right, because it is decreasing to f of c, it is increasing, it is from f c it is increasing after f c, right. So, it is decreasing and it is increasing. So, c is there. So, now f of x will be greater than or equal to f of c for every x. Okay. So, that means that would give us that f x has a local minimum at x equal to c. That is clear? Okay. So, similarly, we will prove 2 and 3. Only the sign changes will occur. Similarly, the inequalities will be changed there. Fine. So, now we can really formulate how to use this information to test for local maxima and minima, but only at the critical points. So, let C be a critical point of f of x. So, this domain we forget, critical point of f of x. So, of course, C should be inside the domain, but we can think of this to be not only interior point, but the end points also. Now, for the interior point, that theorem is applicable, and we have already discussed about left and right end points. So, we formulate like this. Let C be a critical point of f. F prime x changes sign from minus to plus at x equal to c would give that x equal to c is a point of local minimum of f of x. Minus to plus gives local minimum, and f prime x changes sign from plus to minus at c means the critical point c is a local maximum of f x. Now, at the end points, say x equal to c is a left end point of the domain of f x. If f prime x is less than 0 on c to c plus delta, that is the only possible neighborhood, relevant one. C minus delta to c is not relevant here. So, if it is less than 0, that means f will be, it is less than 0. So, f will be decreasing, then there is a point of local minimum of f x, okay, at x equal to c. See, if f prime x is less than 0, so that means f is decreasing at the end. So, this is our A. So, it is decreasing means right end it will be going like this. So, this should be a local minimum. Now, if it is bigger than 0, so that means it is increasing, right. So, it is f prime x is bigger than 0 on c to c plus delta, and c is a left end point. So, what happens? It is bigger than 0. So, it is increasing, f is increasing. So, that would give, there is some problem here. You have f prime x is less than 0 on c to c plus delta. So, this is your c, this is c plus delta. Here f prime is less than 0. So, that means f will be decreasing, right. So, it would look something like this, right. And if f prime x is bigger than 0, then f will be increasing. So, this will be applicable. Then it should be the other way around, it should be local maximum and this should be local minimum. We can find from the picture if there is some problem, of course. So, you look at the picture, here you have the left endpoint A, what is happening? F prime is bigger than 0 on the right neighborhood. So, once that happens, it is bigger than 0, that should be a local minimum here, right. So, positive to the right neighborhood means it should be local minimum. Is that clear? So, let us say it is positive. So, if it is positive, then it should be local minimum, and if f prime x is less than 0, it is this way, it should be decreasing. So, it should be local maximum, and suppose it is a right endpoint on the other side, here it is a right endpoint, then f prime x is less than 0, one of the neighborhoods is only relevant, c minus delta to c. So, c minus delta to c is relevant. Now, f prime x is less than 0. So, f is decreasing there. So, that means it will decrease to this. That means this should be your local minimum, that is correct. Now, if f prime x is bigger than 0 on c minus delta to c, then it is increasing. So, to this way f of c. So, that means at c it should be a local maximum, that is what it says. Is that right? So, you have to really remember this thing, but as you see there is nothing much to remember, you can simply resort back to your geometrical notion and set it right. Okay. So, let us apply this test on some problems. Say first example, we are asked to find all local maxima and minima for the function f x equal to x plus sin x. So, if you plot the graph, it would look something like this, but it will be misleading sometimes, because these points may look horizontal, sometimes they are not. Okay. So, we will find out analytically what happens. Now, this function is differentiable on the whole of R, okay, and its derivative is 1 plus cos x. Then we should find its critical points. So, when is it 0? 1 plus cos x equal to 0 means cos x equal to minus 1. So, one solution, first solution is pi, x equal to pi, but due to periodicity there will be 2n pi added to it. So, all our critical points are here, 2n plus 1 into pi for n belonging to z, that is n is an integer. So, this will have your phi, 3 pi, 5 pi and so on the one side. On the other side you have minus pi, minus phi minus 2 pi minus 3 pi and so on. So, all these points are the critical points of this. Now, at these critical points we must find out whether there is a maxima or minima or something, right. So, you have to look for the change of sign in f prime. Now, what happens for f prime? If you take f prime at any of these points, that is 0. Now, suppose you take any x which is not of the form 2n plus 1 into pi, then it will be 1 plus cosine of that something, right, c, which is not equal to 2n plus 1 pi, but cosine of c is always remaining between minus 1 to 1, right. This lies between minus 1 to 1, and this is equal to 1, equal to minus 1 at those points, otherwise it is not. So, it is not equal to minus 1, that means cosine c here is greater than minus 1, but can be equal to 1 when c is not one of these points. So, when you take 1 plus cosine c, it is always bigger than 0, right. So, since it is bigger than 0, the function is increasing throughout. So, if it is increasing throughout, it does not have a local maximum or local minimum. So, even these critical points are not points of extremum, that is what we conclude, fine. Okay. So, this has no local maxima or minima. Let us take another example. Suppose f is a function defined on the closed interval minus 1 to 2, and it is given by f of x equal to x to the power 1 by 3 times x minus 4, which is x to the power 4 by 3 minus 4 times x to the power 1 by 3. Fine. So, this is also defined everywhere. Negative also it is negative, positive it will be positive, 1 by 3 is there, and x minus 4 takes care of the other, whether it is less than or greater than 0. Okay. Now, we are asked to find the intervals where the function is increasing or decreasing, and basing on that find the local maxima minima, find the absolute maxima minima of this function f x. Okay. So, for this we have to first we take the derivative. Okay. So, the derivative is f prime x equal to, it is x to the power 4 by 3 minus 4 times x to the power 1 by 3. So, it is 4 by 3 and x to the power 4 by 3 x to the power 1 by 3. This 1 by 3 should be here, right. 4 by 3 times x to the power 1 by 3, 3 x to the power 1 by 3 minus x to the power 1 by 3. So, that is again 4 by 3 x to the power minus 2 by 3, that is how it looks. Okay. So, where is it equal to 0? What are the critical points? We see that this is on the top. Okay. So, it vanishes for x equal to 1. At that point this is also 1 and the x to the power 1 by 3 is also 1. So, it vanishes for x equal to 1, and it is not defined for x equal to 0 because x to the power minus 2 by 3 is involved, right. So, this x to the power 3 is on the top now. Okay. So, the critical points are now 2, not only 1. It is 0 for x equal to 1 and it is not differentiable, the function is not differentiable at x equal to 0. So, we have 2 critical points. Of course, the function is continuous on the closed interval minus 1 to 2. So, we can apply our earlier reasoning. Now, at these 2 points what happens to the function? It divides again the whole of minus 1 to 2 into intervals. One is minus 1 to 1, another is minus 1 to 0, another is 0 to 1 and another is 1 to 2. So, there are 3 intervals you get, fine, because there are 2 critical points. Okay. So, we consider these 3 intervals and find out whether the function is increasing or decreasing in these intervals, fine. So, now when you take minus 1 to 0, it has the same, because it is 0 there, f prime is also continuous except at 0, that point where it is not defined. So, there is same behavior throughout these intervals of the function. If it is increasing throughout the interval. If it is decreasing, it is decreasing throughout the interval. That behavior can change from these 3 intervals to intervals. So, inside minus 1 to 0, if you take f prime of minus half, it is really less than 0. So, that gives us that f prime is less than 0, is negative in this interval minus 1 to 0. Of course, you can directly argue now. And similarly, f prime at half is also less than 0. So, on 0 to 1 this is also less than 0, but f prime 3 by 2 is greater than 0. So, on 1 to 2 it is greater than 0. So, there is only change of sign at 1, there is no change of sign at 0, right. And this sign change happens like this: f prime is minus on minus 1 to 0, also minus on 0 to 1, at 0 it is not defined, and plus on 1 to 2. Okay. So, it is decreasing in minus 1 to 0, decreasing on 0 to 1 and increasing on 1 to 2, right. So, that means f x is decreasing throughout minus 1 to 1 except at that point 0 where it is not defined, and increasing on 1 to 2. So, it does not have a local extremum at x equal to 0, because at 0 there should be a change of sign, but there is no change of sign here, right. It is same minus throughout from minus 1 to 1 itself except that 0, neither from minus to plus nor from plus to minus from the when you go from left side of 0 to right side of 0. But at 1 there is some change, right. So, at 1 it is f prime is changing sign from minus to plus, right, at 1. So, there is a point of local minimum at f of x, right. F is decreasing on the left of it and increasing on the right of it. So, f has a local minimum at x equal to 1, and the value of this local minimum is of course f of 1, which is minus 3. Then at the end points we have to also consider the end points, right, it is a closed interval. So, we have the end points now minus 1 and 2. Now, at minus 1 only the right neighborhood is relevant, left neighborhood is not relevant. So, what we do? We see to the right of x equal to minus 1. To the right of it, it is minus 1 to 0, where the function is decreasing, that is f prime is less than 0, right. So, since f prime is less than 0, it is decreasing, f is decreasing at the end point, left end point minus 1. So, at minus 1 there is a local maximum, okay. That is what it says, and the local maximum value is f of minus 1 equal to 5. You just substitute minus 1 there and get. What about the other endpoint? We have the endpoint as 2. So, at x equal to 2 only the left neighborhood is relevant, and on the left neighborhood, which is 1 to 2, f prime is bigger than 0, f is increasing. So, f is increasing like this, again there is a maximum there, right. So, there is a local maximum at x equal to 2, and its value is of course, it is not simple integers like earlier, it is minus 2 to the power 4 by 3. So, now you can compare all these values, whatever maximum minimum values you have got, and find out your absolute maximum and absolute minimum. So, for comparison let us list them out. F of minus is 5, f of 0 is 0, 0 was also a critical point, f of 1 equal to minus 3, f of 2 equal to minus 2 to the power 4 by 3. So, had you just taken the critical points without coming to local maximum minimum, you would have got also the same thing for the absolute maximum or minimum. But at the end points we will not say they are critical, they will be taken as end points and evaluated. So, critical points are 0 and 1, end points are minus 1 and 2. So, evaluate all those points and compare them, find out that the absolute minimum is minus 3, which occurs at 1, and absolute maximum is 5, which occurs at minus 1, right. So, that is how we will be proceeding to solve problems basing on information of the first derivative, coming to increasing decreasing nature, and then thinking about maxima minima. Okay. So, let us stop here.